This is section 1.4, functions. In this section, we're going to introduce functions and we're going to talk about some of the common properties of functions. And so our learning goal for this section is to define, evaluate, and use functions. And some of the specific objectives we'll be looking to achieve are to determine whether relations between two variables are functions, 2, use function notation and evaluate functions, and 3, find domain and range of functions. So before we get too deep into things, let's just start briefly talking about something we've been using for a long time, such as the equation y equals x squared, or any other equation. Really, all equations are just a way in which we make a relationship between two values. In this case, we're making a relationship between x with y, in which y is just going to be the quantity of x squared. So essentially, that's all an equation is. It's just a relationship between two values. One of them is an input, such as our x, and the other one is an output. And we also know that we can represent these in a couple different ways, such as a coordinate. And for this ordered pair, we plug in an x value and we get back a y value. And we've done different things with that, like plotting points and finding graphs of equations from that. And so this equation and many of the equations we've already seen before are great examples of functions because we have an input, which we commonly associate that with x, and we have an output, which we usually use the letter y to represent. And so like I said, you've been using functions for quite a bit now, but let's actually go ahead and formalize and come up with a definition as to what is a function. So a function is just a relation that assigns each element in a set, or set A, to exactly one element in set B. And although this definition sounds a little bit clustered, I want you to realize that we've already been working with functions, we've seen many different types of functions, and in just a second we're going to look at a couple examples where we're going to break down what this really means, and we're going to gain a full understanding of what a function is. Now, to elaborate on this definition of a function, we can list out some of these characteristics. And in just a second, we're going to see an example where we pinpoint each one exactly so that we can get an idea of what they really mean. So here, in order to get a good understanding of these characteristics, let's go ahead and look at the example y equals x squared. And in our definition and in the characteristics listed below, we often reference set A and set B. And for this example, set A is just the x values we can use for this equation, and set B are just the y values that can result from this function. And so the first characteristic says that each element in set A must be matched with an element in set B. And if you think about it, for whatever x value I decide to plug in, I'm always going to get a y. It's never going to be the case that I choose a number for x that won't give me a corresponding y value. I can go ahead and choose x equals 1 or x equals 2 or x equals 3, whatever number you want, but regardless of that value of x, you're going to get an output. And that's all that first characteristic is saying. And so the second characteristic says an element in A cannot be matched with 2 or more elements in B. Now all that means is that one input can't give me 2 separate outputs. So for example, if I plug in 2 for x, I'm going to have 2 squared. That's always going to give me 4. It's never the case that sometimes it's going to give me 8 or sometimes it's going to give me 6. Every input has exactly one output. And the last bullet point says that 2 or more elements in A may be matched with the same element in B. That just means that it's possible for 2 different elements in A, so 2 different input values, to give you the same end result. For example, here we could have x is equal to 2, which would give us an output of 4, but we can also plug in -2, which also gives us 4. And that is a perfectly fine characteristic of functions. Okay, so for this first example, we're asked to determine whether the following relation represents y as a function of x. So what we're going to do is just check those first 2 characteristics we just talked about and see if they hold true for the values we're given. This is a standard xy table, but if you want to think about it in terms of sets, your inputs or your x values are your first set, and your outputs, y values, are your second set. Okay, and so again, to determine if this is a function or not, we're going to go ahead and look at each of those characteristics. So the first characteristic says that each input value is matched up with an output value. So here our input 2 is matched up with -2, 3 is matched up with 0, 4 with 1, and 5 with -1. So we can say that the first characteristic is satisfied. And the second characteristic says that every x value is matched up only with one y value. So this 2, it is only matched up with a -2. I don't see any other 2's down here, and so we are good there. Likewise, 3 is only matched up with 0, 4 is only matched up with 1, 5 is only matched up with -1. And so it seems like we're good there, and we can say that the second characteristic is also satisfied. And since both of those characteristics are satisfied, we can conclude that this is a function. So for this next example, we're going to do the same thing and determine whether these two are functions or not functions. And again, to do this, we're just going to look to see if they satisfy the first two characteristics we talked about. Now, although it looks a little bit different, we're still looking at our x and y values, so inputs and outputs. And so the first characteristic says each element in set A, or our inputs, must be matched with an element in B. So each one of our inputs does have a matching output, and so the first characteristic is satisfied. And for our second characteristic, each element in A, so our inputs cannot be matched with two or more elements in B, and so we have 2 matching with -2. I don't see any other 2's matching up with a different value. Likewise, 3 matches with 0, and there is no other 3's. 4 matches with 1, and 5 matches with -1. So it looks like we are good here as well, as there is no x value that matches up with more than one y value. And so that we can conclude that this first part is in fact a function. So if we look at part B, again, it's pretty clear to see that each input has an output since we're given ordered pairs. So our first characteristic is satisfied. Now our second characteristic, again, says that an element in A cannot be matched with 2 or more elements in B. Here, however, we do have a case that doesn't satisfy this. Notice that 2 shows up as an x value or input value 2 times, and one time it goes to 0, and one time it goes to -1. And therefore this x value of 2 is being matched up with 2 different elements in B. Therefore this is not a function. So we'll be working with examples of relationships and determining whether they are functions or not a little bit more later. But for now, I want to talk about what are the different ways of representing functions. And as you can see, there is 4 different ways: verbally, algebraically, numerically, and graphically. And I have an example up on the screen for each one of those. So as an example, the function y equals x squared, well, that would be our algebraic representation, and that might be what we're most used to seeing. But we could also represent this verbally as the output is the square of the input. And it represents the same thing because our output is y, which is obtained from the square of our input x. And we could also represent this function numerically with, for example, a table of values, which we've done before, where we match up inputs with outputs. So -2 is matched up with 4, -1 with 1, so on and so forth. And then finally, graphically, which we've also done before, it's just representing this function by using a graph, which we obtain from all the ordered pairs from our numerical table. And so now that we've learned the different ways of representing functions, let's quickly review function notation. So most of the equations we've worked with so far have been of the form y equals x squared plus 2, for example. But when we use function notation, we're actually going to represent that same equation as f of x is equal to x squared plus 2. And all that does is to help other people realize that the equation we're working with is in fact a function. And really the only change is what it looks like. We're getting rid of this y, and we're using the f of x in its place. And that tells us that this equation that we're looking at is a function. And so to summarize, function notation is just a different way we're going to do the same thing. So if you want to think about that in terms of your ordered pairs x and y, really we're just going to call that now x and f of x. We're still talking about the exact same thing though, where x is going to be your input and your output. It's not going to be called y anymore. We're just going to call that f of x. So let's go ahead and evaluate some functions using this function notation. We're given the function f of x is equal to 10x minus 2, and we're going to go ahead and find what f of 2 is. Now all that means is that in our function where we have this x value, we're just going to go ahead and replace that with a 2. And so f of 2 would be represented as 10 minus 2 squared. And so now it's just a matter of doing the arithmetic to simplify this out, and we get 10 minus 4, which we know that is 6. And so what this is telling us is that our function evaluated at 2 gives us an output of 6. And so if we look at f of negative 4, again, all that's saying is look at your function f and replace the x with a negative 4. So when we write this out, we're just saying our function evaluated at negative 4 is 10 minus negative 4 squared, which we can simplify to be 10 minus 16, which is equal to negative 6. And so our function evaluated at negative 4 gives us negative 6. And so for this last one, although it looks a little bit different, we're going to continue to do the exact same thing we've been doing. So we're going to replace all of our x's in our function with x minus 1. So f of x minus 1 is just 10 minus, here where I have my x, I'm going to go ahead and put in my input, x minus 1, quantity square. And we could definitely simplify this out a little bit, but for now I just want you to realize that whatever we have inside the parentheses, function notation, is just what we're replacing our x with in our equation. And so the last thing we got to talk about in this section is domain and range of functions. As you can see, the definition of domain is a set of all values of the independent variable for which the function is defined. And all that means is you're looking at all the possible inputs. So if you're looking at an equation, what values of x can you choose to input? Similarly, our range is just a set of all possible output values, or in an equation, all possible y values you can get. And so you can think of domain as all the possible input values you can have in a function, or all the possible x values, and range likewise can be all the possible outputs or y values. And one of the focuses going forward is going to be able to determine the domain and range of functions. So just being able to figure out what are all the possible input values we can use and what are all the possible outputs. So let's quickly look at an example where we determine the domain of a function algebraically. And remember, all domain is essentially just a list of all possible x or input values for a function. So actually the best way to find the domain is by looking for things that don't actually work. So there is two restrictions. Our first is that we don't want input values that are going to cause a 0 in the denominator of a fraction. That would cause us to be dividing by 0, which is illegal in mathematics. And the second domain restriction is we don't want to have any input values that are going to give us negative numbers under square roots or any other even roots like a fourth root or a sixth root. And the reason for this is for now we're sticking only with real numbers, and so we cannot have negative under square roots. So for this first example, we have the function f of x is equal to the square root of x minus 4. And we need to try to evaluate what the domain is. So since I have a square root, what we need to do to find a domain is make sure that whatever's under the radical is never negative. So in this case, we have x minus 4. And we never want that to be negative, otherwise we're running into complex numbers, and we don't want that for now. So we're going to make that always be greater than or equal to 0. And if I solve for x here, add that 4 to the other side, this is telling us that x can be any value greater than or equal to 4. And that's exactly what our domain is. So our domain is any value as long as it is greater than or equal to 4. So for our next example, we have f of x is equal to x squared divided by x minus 3. And the thing we have to watch out for here, we don't divide by 0 since we have a fraction. So we don't want this x minus 3 to equal 0. And the value of x that would do that, if we solve for x, would be 3. So we actually cannot use x equals 3 for this function. But we can use whichever other x value we want. Again, as long as we are not using x equals 3, because that would have us dividing by 0. And so we can say that our domain is all x values except x equals 3.